Hello, everyone. So we are 3DY session 3. So I'm Isaac Cho. I'm the session chair of the 3DY session 3. So we have 4 presentations. The first 2 in person, and next 2 is for the virtual presentation. So first paper is actually from my group. It's the crossing race evaluation of bimanual midway selection techniques in an immersive environment. So DongHoon Kim is the presenter. He will present this work.
Hello everyone, I'm Dongyun Kim, PhD student at Utah State University. This time I'll introduce my paper, Crossing Ray Evaluation of Bimanual Media Selection Techniques in an Immersive Environment. Okay, let's start from the motivation. The commonly used selection technique in virtual reality that requires a visible target object. A user has to aim the target object first. After that, they can have selection. And in some navigation techniques, such as teleportation, a user that also requires to select a destination on the ground object. Unfortunately, that kind of selection technique is useless when a user has to select a point in midair, like a space or middle of the sky. There is no selectable object, and there is no ground. There is just space. So we motivated this limitation. How we can make it possible? In previous, there are media navigation technique based on parabolic ray and one hand. A user can select a position on the virtual ground level and elevate its height. This technique makes it possible to select the media position, but it is not straightforward, especially when a user selects a high or lower position. We set this technique as a baseline, and we found a better way. And we found the intersection-based bimanual technique called ISIS. This technique utilizes a crossing point between the 2 rays. This technique is studied for selecting occluded object, but we focus on the possibility that can select a point on a ray. So we designed 4 variations based on the ISIS. The first variation is a simple ray. There are 2 rays, and when the rays are intersect, a sphere indicates the crossing point. This sphere is the selection point, so user can point the middle position as locating that sphere. And the next variation is simple strip. From the previous variation, we add 1 meter strips on a ray to increase the depth perception. A user can measure the distance using these strips. And next variation is precision strip. From the last one, we add 1 feature. A user can select 1 strip. Using the joystick, user can select the strip. When a user pushes it, the selection strip goes further, and pull it, the strip comes closer. But the crossing point in this technique can only be located in the strip on the selected range. So this can help the user have selection more accurately than previous one. And next one is the cursor sync. From the previous variation, this has 1 more feature. With this technique, a user doesn't have to aim far away. Instead, that user just have to make an intersection point in the first strip. But the crossing point in the selection is in the selected range. The intersection points position in the first strip and the crossing point in the selected strip are synchronized. So with this technique, user can select an exact position in the first strip, even if the target is far away. And to evaluate our techniques, we designed 2 types of media selection tasks. The first one is selecting a media position in front of an object. A participant has to select 1.5 meter in front of the box object with a given technique. And the second task is a media position where object was. In this task, a red sphere is shown, and this sphere is disappeared after 1.5 seconds. So a participant has to select the position after the red sphere has disappeared. Okay. During the experiment, we measure these things: selection time to investigate the techniques, the selecting speed, and error distance to know the accuracy, and NASA TRX and user experience questionnaires to investigate the user experience. Based on the techniques and experimental task, we set this hypothesis. To investigate the selecting speed, we set hypothesis 1. Simple A and simple strips are expected to have faster selection than the others. And second, cursor sync is expected to have a faster selection than precision strip and one hand. And to investigate the accuracy, we set third hypothesis. Precision strip and cursor sync are expected to have the higher accuracy compared to the others. And simple strip is expected to have higher accuracy than simple A and one hand. And lastly, we said hypothesis about the user experience. Simple strip, precision strip, and cursor syncs are expected to provide a better usability and less workload than simple A and one hand. We had experiment with 3 target distance, 3, 6, 9 meters, and 5 techniques with 20 participants using MetaQuest 3 device. From the first task, the selection time result shows that simple A and simple strip provide the fastest selection on all distances. And precision strip and cursor sync are significantly delayed as the target distance is further. So this result supports hypothesis 1 and partially supports hypothesis 2 about the faster selection. From the error distance result, we know the simple A and precision strip shows better accuracy, that means less error distance than others. But this result does not support hypothesis 3 and 4 about the accuracy. And this is a user experience result. This shows that the precision strip and cursor sync technique provide a better user experience than others. For the every subject, these techniques get lower score when it's better and get higher score when it is better. So this result partially supports hypothesis 5 about the usability and workload. Discussion about the task 1. From the task 1, we know that in general, bimanual techniques are faster than one-hand techniques, and strip selection causes a slower selection time. And adding visual aids does not improve accuracy. And lastly, precision strip and cursor sync provide a better user experience than others. And task 2, that is the task for the selecting where the last pair was. The result shows, the selection time result shows that simple A and simple strips are the fastest technique on all distances. And precision strip and cursor sync are significantly delayed as the distance is further, same with the task 1. And this result supports hypothesis 1 and 2 about the selection time. And error distance result shows that at 3 meter case, all bimanual techniques, the crossing ray techniques, are more correct than the one-hand techniques. And at 6 meter, simple strip and cursor sync is more correct than simple A and one hand. And 9 meter, precision strip, cursor sync, and one hand are more correct than others. And because the simple technique, the simple A and simple strips become inaccurate as following the target object is further. And it can be more with the target, it can be more with the further target. So this result partially supports hypothesis 3 and 4 about the accuracy. And user experience result shows that all crossing ray or bimanual techniques provide a better user experience than one hand. So this result partially supports hypothesis 5 about the usability and workload. So discussion. From the task 2's result, we found that in general, same with the task 1, bimanual techniques are faster than one hand. And accuracy is decreased as the target is further, and strip selection on the precision strip and cursor sync can increase the accuracy. And the strip selection is significantly useful on far away target. And lastly, bimanual technique can improve the user experience. So conclusion. From this study, we know that media selection technique with crossing ray provides better selection speed, accuracy, and user experience than one-hand-based technique. And visual ads, such as the 1 meter strip, can make better performance, but it is not significantly effective. And lastly, selection support features such as selecting strip or synchronized point make better performance, especially when a user selects a far point. And we suppose our technique can be used for a media approach for some kind of teleportation or media reporters. Okay. Thank you for listening.
Okay, yeah. So, yeah, we have plenty of time for the questions. Are there any questions from the audience?
Hi, I'm Tim Weisker from RWTH Aachen University. So I'm one of the co-authors of the one-hand technique that you selected for the baseline comparison.
Sorry.
So no need to sorry. I just wanted to know, like, why did you choose this particular technique? Because the paper had 3 different techniques. So why was it this one of the 3?
Yeah.
And I just wanted to add to the discussion that we designed this technique particularly for navigation scenarios.
Yeah.
So it's deliberately a bit slower and offers a lot of preview mechanisms that the user is prepared, so pre-travel information as we call it. So there's a lot of interaction workflow involved that the user doesn't get disoriented. So maybe could you briefly just comment on the selection of this technique and maybe the alternatives and the decision process that went into this?
Yeah, actually, thank you. Sorry, and okay.
No need to sorry.
Yeah. Actually, as you know, for teleportation, you have to select the position, the destination position. So even if that technique is aimed to the navigation, but it's one of the selection technique. It can be used as the selection technique, the position selection technique. So that's why we choose this paper, your paper on our study. And there was 3 different techniques to handling the media position, but actually that has many steps. First one have to select the ground level position first and then evaluate it. And other things is teleport first and then they elevate that position. But this technique control that the position on the XY plane and the height at the same time. So, but our techniques, such as these techniques, also handle the position on the plane, on the height at one time. So that's why we select that your simultaneous technique. Yeah.
So I would maybe like to add to this discussion, like for one-handed mid-air selections, that there might be other alternatives that might be more suitable for the scenario of really selecting mid-air objects. You had these target objects in mid-air that you aim to select with these 2 rays.
Yeah.
So I thought about maybe as a one-handed comparison, as the representative of a one-handed technique, you could also maybe have a look at these depth cursors, for example. So you have like a ray coming out of your controller with a controllable sphere that you can manipulate in depth, something like that. So I think this might be more suitable for this classic mid-air selection scenario where you exactly have this target sphere, whereas I would say the techniques that we've developed are more bound to the navigation context. So if you're going further, that would be my advice, maybe not to use our technique as the representative for one-handed navigation. So I think that's not what we intended with publishing this paper.
Thank you for comment. Yeah.
Thank you very much.
And we can talk about that later. Right, so next presentation is from the research to practice, survey and taxonomy of object selection in consumer VR applications. Mykola, Maslych, right?
Yes.
Yeah. So.
Thank you. I started the slides, but I don't see them up. Yeah. Oh, thank you. Hello, everyone. My name is Mykola Maslych. I'm a PhD student, PhD candidate at the University of Central Florida. This work was done in collaboration with people from University of Copenhagen, and the title is Survey and Taxonomy of Object Selection in Consumer VR Applications. So selections are some of the most common interaction techniques in virtual reality. And as researchers, we focus on accuracy, speed, and usability of these techniques. To show the effectiveness of our specific techniques over alternatives, we tend to design environments where our new technique will outperform the alternatives. This approach improves usability in specific contexts, however, has some drawbacks. The first issue is that constrained experimental setups lead to difficulty in assessing the potential impact of our new techniques. And it's unclear whether UX would actually improve because the selection scenarios in practice might not leverage the same set of strengths that makes our techniques better in experimental setups. This leads to a lag between research and practice because higher complexity of our techniques and the higher number of them is more difficult to get picked up in consumer applications. So this leads to slower adoption.
Hello, everybody.
So the purpose of this work is to identify the gaps between research literature and consumer VR applications in VR selection techniques, and then begin bridging these gaps with a taxonomy based on specifically selection in consumer applications.
And this work is also done with my collaborator.
We contributed a taxonomy and initial analysis, which is in the paper, and also a tool that is hopefully useful for students, researchers, and practitioners, which is an open source database of 1,300 plus selection scenarios from 200 plus consumer VR applications. To establish the taxonomy, we first vetted the applications that we will review. Then we looked at existing taxonomies to get the definitions of all of the existing categories of selections. In phase 3, we did video reviews of VR application walkthroughs, saved the timestamps of the videos with unique instances of selections. In phase 4, we created our new taxonomies based on the patterns and definitions that exist and augmented them with the patterns that we observed during the review. In phase 5, we validated the taxonomy using inter-rated reliability scoring. And more of this is in the paper. This is the resulting taxonomy, has where and how components. Where is about the task, so where in the environment does the selection occur, and how is about the process, so how does the selection occur. Using this taxonomy, we classified all of the previously extracted selection instances in consumer applications, and that's the database that we present. Now let's highlight some specific categories from this taxonomy. So the reference frame is the coordinate system in which selection targets appear. It can be either environment referenced or body referenced. Environment reference objects move independently of the user, while body reference objects move within the coordinate system of the user's head, hand, or the estimated torso position. I will show some concrete examples in a few slides. The main categories of the target types are 2D and 3D objects, and we also identified 3 types that deserve to be included because they happen so frequently in consumer applications. These are avatars, storage units, which basically you can attach other selectable objects into, and also discrete configurations, which are selectable states of the objects, such as the discrete positions or rotations of knobs and levers. So to make everything clear, in example 1, the user interface with the selectable buttons move within the user's HMD. So as the user rotates, it moves together with the user. So these are head reference. In example 2, there are selectable storage units in an inventory, and this inventory is moving with the user's left hand. So the selectable storage units are in the hand reference.
Hello everyone, my name is Yu Wei, and I'm honored to present my team today to present
In example 3, objects in inventory system follow the user's estimated torso positions, so they are torso referenced. And then in example 4, the user is setting a handheld slider into one of the selectable discrete configurations, which is a type of selection that we identify here. And yeah, so these are the examples. Now for the how taxonomy. So this describes the selection technique and what happens as a result of selection. The first is the outcome. It can be either acquisition or system control. Acquisition is when user ends up holding the object as a result of selection. And the system control is when the user doesn't and the change is internal to the system. Or this can be, for example, changing the settings in the VR game. Next interactor is the proxy object used in the selection process. Everyone is familiar with Ray and virtual hand, so I'll advance to the newer one, handheld object. An object is considered a handheld interactor when it was previously acquired specifically for the purpose of selecting other things. Weapons such as swords and guns are handheld and used for further selection. Levers and knobs are handheld and used for selecting discrete configurations. Objects that will be inserted into storage units are also handheld interactors. I will have some examples of these in a few slides. It is crucial to understand the two stages of selection process, which is indication and confirmation. Indication stage determines a specific object from a set of selectable objects within the environment, and this is most commonly done through pointing and intersecting a virtual hand. And then once an object or multiple objects are indicated, the confirmation stage validates the user's actual intention to make the selection. For example, by pressing a physical button on a controller. The standard selection indication techniques are pointing and intersection. Aiming techniques involve handheld proxy objects that are used to indicate another object. Here we define aiming under shooting and throwing. So shooting involves a scope that must be held eye level to aim, similar to an aperture technique from the past. We do not include guns with visible rays in this category, so this is a separate, specifically eye level aiming. And then throwing involves aligning a handheld object with the target and the subsequent motion in the direction. Discrete manipulation requires the user to set a handheld proxy object into one of the discrete configurations from a finite set of configurations. And lastly, enclosing requires the user to specify a volume in space, and this volume is likely to include more than a single target object. For confirmation, a method that was very popular in the past is dwelling. So back in the days of phone VR, when we had the Google Cardboard, there were no controllers. And because of that, the user had to maintain head gaze ray intersected with the target for a fixed period of time, and that would confirm the selection. So next for analog and tracked hand types. So they have some similarities and they have some similar subcategories. Physical switches have on and off states, and tracked hands have poses that can represent gesture and non-gesture states. In this sense, they have similarities because transitions between gesture states are similar to transitions between switches on and off states. Click refers to pressing and instantly releasing a physical switch. Continued press release refers to holding down the button while indicating an object. This is mostly used for beginning manipulation or like acquiring an object. And release refers to unpressing a physical switch, which is most commonly used for inserting items into storage units. Pressing motion is also frequent in VR consumer applications, but is not as present in research. It requires pressing an object that has virtual physics, such as virtual buttons, along its degree of freedom, and which is different from automatic confirmation, where no explicit input beyond just the initial collision is required to confirm the selection. So just the indication stage with automatic is enough. For example, in the selection of touching UI elements in two-dimensional UIs in VR. In example 1 from before, proxy handheld object is the interactor, and the indication method is discrete manipulation. In example 2, a virtual hand representation requires to press a virtual button to confirm a selection. And in example 3, a bounding volume is used to enclose target objects, and releasing the trigger button confirms the selection. We have much more examples and the whole database to show examples based on the taxonomy. You can look, you can find it. I'll have a QR code for it at the end. So now for a little bit of the summary. So throughout this review, we found areas where some things don't work perfectly in consumer applications, and I think as researchers, we could help them be improved. So here are some specific areas. Selection of body reference objects such as on-hand UIs and torso items are very common in games, and a lot of times this leads to people actually colliding controllers or hitting their own body with the controllers. So as researchers, we could help improve that, hopefully therefore improving UX in consumer games. Selection of discrete configurations are also frequent, so this is stuff like sliders, knobs, and so on. And we could improve the mapping between the user input and the movement of these things because, frankly, as of right now, they're pretty janky. You move stuff and it kind of jumps around. So we could work on improving those. And hand tracking is also becoming more common, but for mainstream adoption, we need to make it so that it works with both locomotion and selection at the same time. Right now, there's a lot of false positives when hand tracking is used for both of these modes of interaction. I used to have a demo for the website, but now we have a screenshot. We have a web page where you can actually select anything based on the taxonomy, filter, and then find instances with YouTube links to time-stamped examples of where exactly certain selections happen. We hope that this tool will be useful for students in 3D UI classes, for researchers and practitioners to quickly look up implementations of various techniques based on the taxonomy. Here's the QR code. That's the end of my presentation. I'm ready to answer any questions you guys have. Thank you.
Thank you for the presentation. So questions? May take like 1 or 2 questions.
Thanks for the talk. Seems like a very comprehensive taxonomy, so appreciate the work. My question is, in the survey of software applications that you did, what percentage were games and what percentage were more serious applications? And do you think that makes a difference?
Yeah, so approximately 10%, thank you for the question. Approximately 10% of the applications were modeling apps, and they have much more variety of different techniques. For example, enclosing of multiple objects, which is far less likely to be in games. So modeling applications are actually built into some of the existing games where you can create the environment and let other people play in it, and those include a larger variety of those. The database is skewed more towards the representation of what's in games, but we included those anyways so that we show the variety of, yes, some of the techniques that we research do actually occur in modeling applications in the wild as well.
Okay, any other questions? So I actually have one question. So this one is based on like head-mounted display games.
Yes.
But it's not common anymore. A long time ago, there is like non-HMD based games.
Mm-hmm.
But do you think like you can use the same taxonomy or?
So I think so we restricted it to only HMD based. Some of it will apply, not everything, because one of the things is that, yeah, hands need to be tracked, and it's either hand tracking or controllers. Without those, the taxonomy mostly doesn't work. So some parts of it will apply, but not everything.
All right.
Thank you for maybe important, if overdue, taxonomy of selection techniques. I was wondering about the two-dimensional analogs. I know you weren't trying to be skeuomorphic, but in a 2D GUI WIMP idiom, for instance, shift-clicking toggles selection set membership. And I was wondering if there's a 3D analog for that, if you considered it. And likewise for modern content creation layers, like tracks in an audio interface or layers in a 3D interface. there's solo and mute equivalents for picking something out of the mix and muting everything else, or selectively muting something. And those are orthogonal attributes. And I wondered if there were 3D analogs of those operations.
Yeah, thank you for the question. So this is actually, I think we refer to them overall as modifier keys. So you hold a certain button, and now you have a different functionality, even though the cursor looks the same, or maybe the cursor changes, but mode of interaction is similar. Modifier keys change that. It's pretty common, actually, in modeling applications. So there are some cases of that being used. And in our taxonomy, in the database, we have, it is not shown here, but when you click the additional information box here, you will find modeling applications. For those, we have larger descriptions, and they may actually cover stuff like this. So maybe it requires an additional button press and so on. So yeah, this is an area that is good to research and see how it progresses.
So let's move to the next one. So next one is actually the virtual presentation. So validating eyes-free affordance of on-finger hand proximity user interface in in-situ scenarios. The Shariff, Faleel. So we are going to play the video recording.
Hello everybody. I'm presenting our work titled Validating eyes-free affordance of on-finger hand proximate user interfaces in in-situ scenarios. I'm Shariff from the OV lab at the University of British Columbia, Okanagan, and this work is also done with my collaborators SoonUk, David, and Puran. This work focuses on hand proximate user interfaces. These are interfaces where content is displayed on and around the hand and use single-handed thumb-to-finger interactions to interact with it. This idea is not exactly new. There are examples from early 2000s with the two-lip menu and also the hand interactions on the tin myth. And since then, it also has been looked at under the context of micro gestures or thumb-to-finger interactions. Why would such an interface be of interest? Now, consider the in-situ situation here where Chloe is following a cooking tutorial while wearing her AR glasses. And in this case, the cooking task itself is the primary task. The tutorial and interactions that would happen with the video playback is going to be secondary. It's not the primary interaction. The focus is expected to be on the primary interaction. Now, if Chloe wants to interact with the video playback, she just had to bring her hand up and tap any button that she wants that is displayed on her hand. Now, if she's familiar with what's happening, she doesn't even have to look at the hand at all. If she knows where the play button is, she just taps that particular region of the hand. And she simply goes back to cooking without any disruption. Coming back to HPUI, the visual component allows novice users to easily pick up the interface and use it. They have to just look at the hand and tap it the same way they would on their touchscreens. But unlike the touchscreens, you also have this proprioceptive and tactile feedback, which allows them to interact with stuff without looking at their hands. Now, when they keep interacting with the button, say for example, they keep interacting with the play button again and again and again, over time, they would be able to remember this interaction and do it without looking at their hands. On the other hand, the surface of HPUI is not one flat surface. It keeps moving, and it's also a non-rectilinear surface. So there is a possible interaction between these two components, and which is the focus of our work. To test this eyes-free affordance, we are comparing HPUI with a media interface, where you are directly tapping a button with your fingers. Now, prior research has actually shown that such media interactions also has proprioceptive affordances. It is also one of the more common interaction techniques with head-mounted displays. So hence, we use this as the baseline in our experiment. And these are the four main research questions that we were interested in. First, is HPUI better than media in terms of completion time? Does it have better user preference? Does it require visual attention? That is, does it have better eyes-free affordance? And also, we looked at which hand would be preferable to interact with the menu. So experiment had two factors: the technique, that is HPUI or media, and then the handedness, that is which hand is being used to interact with the menu. Is it the dominant hand or the non-dominant hand. As we are primarily interested in the ice-free affordance of these interaction techniques, we are using a compound task. The primary task, which is attention demanding, and the secondary task of interacting with a menu. In any given condition, the participant would be interacting with the workspace or the primary task with one hand, and they would be interacting with the secondary interface, that is the menu, with their second hand. We treat this as a task that is representative of in-situ tasks that may require your attention while you still have to interact with a secondary digital content or digital menu. I'm going to first walk through the individual components on both interfaces and then talk about what happens in there. First, you have the zoom slider, then we have the color button, then we have an accept button. On the other side, we have the workspace, which can be zoomed in and out with the zoom slider. Then we have a peg that would attach itself to the tip of the index finger with which the participant would be interacting with the workspace. And then we have the holes where the peg needs to be placed in. The active hole is going to be highlighted with a color, with the remaining being in a neutral color. And I'm going to explain the task itself with a video. The zoom slider itself changes the zoom level of the workspace. At the beginning of each trial, the participant has to adjust the zoom slider to the point where the hole is actually open. Then they have to select the right color such that the peg's color matches the active hole. Then they have to place the peg on the hole and select the accept button. That completes a trial, and then they have to do it 3 more times to complete one set. Now if they make a wrong selections, you also get a wrong audio cue. And as you can see, in all 3 stages, zooming, selecting the color, and selecting the accept button requires the participant to pay attention to the workspace. So, if the interface has better ice-free affordance, they would be paying less attention to the menu and more attention to the workspace. The zoom is a continuous selection, whereas the accept button is a more discrete selection. At the same time, these are also simple functions where anyone can quickly pick it up. And these functions remain the same throughout the entire experiment. And then we have the color buttons. And these are more complex buttons that takes more time for someone to get familiar with. So we change this color layout for each condition. We collected data from 16 participants, of 2 were left-handed. For each condition, they had 7 blocks, and for each block, they had a total of 7 sets. In the interest of time, I'm going to talk about some of the more interesting results. First, we looked at the average time to complete one set per block. And our analysis primarily focused on the last 2 blocks. A two-way ANOVA shows that the technique did not have a main effect, but the handedness had a main effect. To better understand what is happening here, we broke down the trial into the separate functions, that is the zoom, the color, and the accept. And then we see the technique had a main effect for the zoom and the accept, but not the color. One should know that both the zoom and the accept are the familiar functions, functions that were easy for the user to pick up, whereas the color function was something that they had to pay visual attention to. It was not something that they were familiar with. One possible explanation for what we see here is possibly that there is a trade-off. With the media interface, you have a visually consistent interface, but you don't have the tactile affordance. With HPUI, you have the tactile and proprioceptive affordance, but you don't have a visually consistent interface. So when it's novice functionality or interactions with unfamiliar interfaces, there is a trade-off. But when it comes to interactions that are familiar to the user, the proprioceptive and tactile affordance allows them to interact more quicker. Then we look at the attention percentage. That is the percentage of time spent on the workspace. Now in this case, the higher it is better. Here also we are focusing on the last 2 blocks. And the analysis shows that HPUI is much significant than media when it comes to the attention percentage. And similar to the completion time, with the attention percentage also, we see that the handedness had a main effect. Same as with the previous analysis, here also we broke down the interactions to the individual functions. And here also we see the same pattern where HPUI is significantly better than the media when it comes to attention percentage. So the key takeaways from our work are the following. The dominant hand is preferred for secondary interactions. And it was the case with HPUI and media as well. The second is that HPUI allows users to lean on the eyes-free affordance. And when it comes to less familiar or novice-like functionality, HPUI and media has similar completion times. Whereas when it comes to more expert or familiar functionality, HPUI actually performs better as the users can lean on the proprioceptive and tactile feedback and need to pay less visual attention. Thank you.
I'm not sure he can take a question or not. Let's try. So any questions to the author? It's on you. Hey, Shariff, you're there?
Let's see if we can connect.
Okay, maybe you can connect. Hello?
Hello, can you hear me?
Yes. Oh no, this one.
I think I can't hear you. Hello, can you say something? Ooh. Yeah, should I start asking the question? I think yeah, I'll wait for a bit then.
Is it because of this?
Yeah, I'll try it again. Can you hear me? Okay, so maybe when I ask the question, you can mute it, and then when like he's answering, you can turn up the volume. Okay, so yeah, thank you for your presentation. And I guess my question is there a reason why you're focusing on like the last two, like the last two trials, or I can't remember how you called it, but like, were you only using the last two trials for your data analysis, or like, was I understanding incorrectly? Ooh.
So, Okay, I mean, so we need to move to the next presentation. So actually, he's on Discord, so he can answer your question to Discord. Okay, let's try that way. Okay. Shariff, please put your answers on the Discord channel. But I can explain. So next one, this is the last one, to exploring the modeling directional effect on steering behavior in VR. So Hai-Ning is the presenter, and we'll play the video.
Hello everyone, my name is Wei, and I'm honored to present my team today to present our research. I'm a PhD student from the Hong Kong University of Science and Technology, Guangzhou. And our team includes Kemu Xu, Yue Li, Lin Yu, and my supervisor, Professor Hai-Ning. Today, I will be discussing our study on modeling the directional effect on steering behavior in virtual reality. Our goal is to understand how steering movement direction influences user behavior in virtual environments, and propose a model that describes these behaviors, which can help improve the design of virtual interface. So first, we need to understand what is steering task. Steering refers to task where user guide or navigate object along a path. This type of interaction is common in tasks such as object manipulation, menu navigation, and moving through virtual environments. Specifically, steering tasks require users to control the movement of an object from starting point to a destination within a confined path or area. Previous work has introduced the steering law to describe and predict the user's performance in these tasks. The steering law is a mathematical model that predicts the movement time required to steer an object along a path, and it's represented by the formula, where the capital A is the path length, W is the path width, and A and B with the lowercase are empirical constants. In other words, the law helps quantify how the path length and width influence the time needed to complete steering tasks. After understanding what is steering task, then we will introduce what is directional effects. Previous work has shown that directional play an important role in user performance during selection tasks, particularly in 2D environments. For example, Boris' team studied the directional mouse movement using Fitts law. The research demonstrated that the direction of movement can significantly affect the time required for user to complete pointing tasks. Similarly, modern work by John, as shown on the right, investigated the effects of movement direction in 2D touch-based pointing tasks. They confirmed that direction significantly influences performance and user behavior, with different movement angle yielding varying time to complete tasks. However, the impact of direction on steering tasks in 3D space remains largely unknown. This gap in understanding is what our research aims to address. Based on the inspiration from the aforementioned previous works, we aim to explore how different steering directions and path features impact user performance in virtual environments, and whether we can model these effects mathematically. Therefore, 4 research questions were proposed in this work, where RQ1 and RQ2 focus on understanding user behavior, such as understanding the effects of directional and how bare-hand steering influence user performance on the different path configurations. And RQ3 and RQ4 attempt to model these behaviors if certain behavior patterns were discovered. Therefore, the first user study was conducted to collect the user's steering behavior data to understand their behavior pattern on the different path configurations and directions. Specifically, in this experiment, participants were asked to complete a bare-hand steering task in virtual reality. They sat in a fixed position and use their hand to move a virtual ball along a straight path in different directions. The task involved moving the ball from the center towards various angles. The different movement direction were relative to the participant's view, with the positive x-axis being the reference original point, which means the positive x-axis refers to the 0 degrees. The setup simulated the real-world steering interaction in virtual environments, where users often need to move objects or navigate in multiple directions. Next, we recruited 24 participants, consisting of 12 men and 12 women. The experiment was designed with 3 key variables: path length, path width, and steering direction. The path length was set of 315 and 415 millimeters, and the path width was varied between 40, 60, and 80 millimeters. Participants performed steering tasks in 12 different directions, with angle ranged from 0 degree to 330 degrees, in increment of 30 degrees. The range of conditions allow us to systematically investigate how different path configurations and directions affect the steering performance in a virtual environment. To better understand and evaluate how different conditions affect user behavior and performance, we used several key metrics to evaluate their impact. This includes the movement time, which is the total time taken to complete the task, the average movement speed, which measured how fast participants steer along the path, and the success rate, indicating whether participants complete the task without discontinuing, and the re-enter time, which shows how often participants had re-enter and repinch the sphere to correct their movement. These metrics allow us to quantify the effects of path length, width, and direction on user performance. After completing our user study, we analyzed the data we obtained. Our results indicated that the movement direction significantly influenced users' steering behavior and performance. Specifically, steering along certain directions, especially at quantum boundaries like 0, 90, 180, and 270, lead to faster and more efficient movements compared to other angles. This was evident in both movement time and average movement speed. Furthermore, our analysis also showed that path length and path width also significantly influence users' steering performance. For example, shorter path lengths and wider paths generally resulted in fewer movement time and quicker movement speed, demonstrating that these factors play an important role in users' steering performance. Similarly, we also can witness that the success rate was higher in the quadrant boundary directions, indicating that participants were more likely to complete the task without error or discontinue in these directions. The re-enter times were also lower for these directions, suggesting that users were more precise when steering along this primary axis. Next, to better capture the effect of movement direction on steering tasks, we developed a model to describe how different steering directions impact movement time. Our model extended the traditional steering law by incorporating a term of directional effect. We called it seat effect. The term represents how movement direction influences users' steering performance. It's modeled as a sine wave function to reflect the periodical nature of steering tasks across different directions. The theta results show that the seat effect had a strong correlation between the predicted and actual movement times. Next, we tested our model using data from study 1 to compare it with the original steering law. As shown in the graphics, our model significantly outperforms the baseline model in terms of fit, indicating a much stronger correlation between the predicted and observed movement time. Accordingly, when we compare the model based on the AIC and the BIC, our model consistently shows better performance with lower AIC and BIC values. This demonstrates that our model not only fits the data better, but also more efficient in terms of complexity. To further verify our model, we conducted a second user study with 12 participants, consisting of 6 females, 6 males, aged between 19 and 26 years. The experimental setup was consistent with the first user study in terms of path length and path width. Moreover, we use different movement direction in this time, which is 45 degrees, 135 degrees, and 225 degrees, and 315 degrees, to test the model's robustness across different set of angles. As shown in the table, our model continues to outperform the original sting law. These results confirm the robustness of our model, demonstrating its effectiveness across different movement directions and conditions. In conclusion, our model demonstrates that path characteristics such as width, length, and especially movement direction significantly impact sting performance in virtual environments of users. The theta model provides a strong predictive framework for understanding these effects and can be used to optimize the design of virtual interface. Future VR applications should prioritize certain directions, such as quandering boundaries, and to improve users' efficiency. Thank you for your listening. I'm happy to answer any question you may have.
So I'm pretty sure like we'll have the same technical issues for questions. So he's actually on Zoom, but he's also on Discord as well. So if you have any questions, please use the Discord. Okay. And actually, this is the last presentation of this session. And thank you for attending this session. And I hope you enjoy the rest of the conference. Yeah, please give the applause to the presenters again.